This video is an introduction to the XP Sheeter. We'll look at setting up a simple fluid sim and then converting it into a highly detailed look, creating these amazing thin sheets. We'll then look at manipulating the various settings for different looks. In this scene, we have this piece of lemon geometry. If we just hit ND, we can see the lines of that lemon. Let's get rid of those, and you can see that we have our lemon, and we've placed it within the utilities folder of our XP system, and it has an X-Particles collider tag on it. So let's just click on that tag, and you can see that we have removed the friction, and we've put a 100% bounce on that lemon. So that's going to be our collider geometry, obviously. So now we have an X-Particles emitter in our scene. Let's click on that. So this emitter is a spherical emitter. If we go to the Object tab, you can see we've got the emitter shape set to sphere, and we've got the direction of the particles. They're being spat out on the plus Z axis. So if we hit play, you'll see there's a ball of particles firing out on that plus Z. Let's just have a look at the emission settings of those particles. So we have the emission set to shot mode, and that shot is going to take place on the first frame and just be a one frame shot. So if we just go forward one frame, there's all the particles. And we have the shot type set to hexagonal, and that means they are being born in an hexagonal grid, which means they're nicely spaced on birth, which means they're going to work well with the fluid solver. So they've got a full lifespan, and we've got quite a lot of speed on there. Look, 269 centimeters per second, and we've got a radius of 2 centimeters. So remember, in hexagonal mode, the radius value dictates how many particles are born. The smaller the radius, the more particles it can fit within the hexagonal grid. The larger the radius, the fewer particles can fit. So with 2 centimeters, let's just see how many particles we're emitting there. Just to note, we'll go to the display of our emitter. Let's go to the hood. We'll show the hood. Go forward one frame, and we've got just under 1,500 particles. All right, so let's just switch that hood off. So what we have here is our particles shooting out towards our lemon and then just bouncing off. And they're rebounding off strongly because we've got the bounce value set to 100% on that collider tag. All right. So this is going to be a fluid simulation. So what we're going to use is we're going to use our fluid solver in the Dynamics tab. Let's go to the Dynamics object, and we're going to use an XP Fluid Effects. The Sheeter object, which is what we're going to use, also works very well with the XP Fluid Flip. But the way in which the XP Fluid PBD works and the way it solves for fluid and the simulation that you get means that it isn't as good working with the XP Sheeter. XP Fluid Effects is by far the more versatile. So we're going to use XP Fluid Effects. Now if we hit play, we're going to have a very different simulation. Let's hit play. So now it's solving this as a fluid, so the bounce is very different. But obviously we've got these really kind of separated globules of fluid. And you can see that they're actually forming these beads quite quickly. Now that's partly because the fluid solver is doing its thing, but also there is an above default surface tension setting set here. So let's just see where we adjust that. So in XP Fluid Effects, the fluid properties like surface tension and viscosity and others, they're controlled within the emitter, not the object. So if we go to our XP emitter, we go to the Extended Data tab, to the Fluid Data, you can see, look, everything is default apart from surface tension. Surface tension by default, if we reset it, is set to 3. And that means that it won't bead as much. Now, with the particles being dispersed this widely, it's difficult to see what difference that surface tension makes. But later in the simulation, it will become obvious. So let's leave it on the default 3 for now, which means it doesn't have much surface tension. Okay, so we have our basic simulation, but what we're wanting to do is simulate kind of a high-speed photography splash on this fruit, and we've all seen these product shots for drinks and the like. So what we want to do is use our sheeter tool to fill in the gaps of this fluid simulation to create a sheet, a splash of water. So let's go to our dynamics. We're going to go to our dynamic objects and we're going to pick an XP sheeter. And just before we play through this, we want an accurate velocity solve in our fluid here. The more accurate the fluid velocity solve, the better results we're going to get with this XP sheeter. So remember, to get a more accurate velocity solve within fluid effects, we just go to the object, and the accuracy by default is set to fast. We're just going to use one of these presets. We'll just put it on high. So it'll take longer to simulate because it's making more calculations under the hood, but those extra calculations are going to make the velocity, the movement of these particles much more accurate. So now let's hit play. It's going to look pretty similar, but we have a more accurate fluid solve. Now let's go to our XP sheeter. Now the sheeter is active, but if we hit play, we're not seeing really any extra particles. There's arguably possibly a few extra ones here, look. So the first thing that we are going to do with our sheeter is start exploring some of these threshold sliders. Because what the sheeter does, it looks at a particle simulation, it looks at two particles that are moving away from each other, and if they are moving away from each other in a way that satisfies all the various different threshold settings that we put, it will spawn new particles in between them and fill in the gaps. And there are various different checks that those two particles have to fall within before they will sheet. There is their density value has to fall within the settings that we set. Their distance apart has to fall within the settings we put here in the hole size. They can't be going over the maximum speed or they won't sheet. And then there are some optional extra checks that we can put in, which we'll explore a bit later. And also the angle at which they are moving away from each other has to fall under this angle limit that we put here. So actually what we'll do is we'll just switch off that angle for now. So it's not checking for the angle. At the moment, all it is checking for is what is the density of the two particles moving away from each other? What is the distance, the whole size of the particles moving away from each other, and what is their speed? Now, what sheeter does, it does its own density calculation. So every particle in this simulation, sheeter is going to calculate and give it a density value. And it's the same principle as the fluid density value. If you have lots of particles very close to each other, they will have a higher density value than few particles spaced a long way apart. So what that means is, if we have it set here, it's only going to sheet particles if they've got a very low density value. So that's the particles on the outer edges of a fluid body, the ones that haven't got lots of other particles close to them. And because we have this density value set so low, it's basically disqualifying the majority of the particles in this simulation from being able to sheet. Most of the particles have a much higher density value. So if we just leave everything else as it is on default and creep this up, you'll see that we start getting more particles. Look, much more particles sheeting now, because we've said that particles with 0 to 46% of the overall density value are allowed to sheet. So now we've included lots more. So when we're doing the sheeter, the first place to start is this max density value. And you want to start creeping it up slowly until you get more and more particles sheeting. And you need to be careful, because the sheeter will just continually make more and more and more particles if the particles in the scene fall within these limits. And so it can get out of control. So you need to treat it with respect. So we're going to creep up this density a little bit more. So now it's including even more of these particles to be allowed to sheet. And now look, we're getting pretty much a continuous sheet completely filled in from our particles. All right, if we reduce this max density a little, we might be able to get mostly sheeted, but with a few holes, which can give us some nice effects. Let's just leave that a bit higher up so we're getting that completely continuous sheet. All right, so everything has been included. So now just let's leave max density and let's move on to the min and max hole size. So what this is saying is it will only sheet between two particles that are moving away from each other if they are within 20 centimeters of each other. But because this is a live calculation, we need to look at it from the beginning. So we can say that all of these particles are within 20 centimeters of each other. They're not moving away from each other quickly enough, so they're always sheeting. But if we start reducing this max, we're going to start getting at the beginning of the simulation particles bouncing off and suddenly not being within that now 10 centimeter threshold. Let's have a look. So now, yeah, look, we've now got some gaps. And of course, these are continually moving away from each other, so the holes are getting bigger, and these particles are never getting within 10 centimeters of each other, so they're no longer sheeting. And so they're getting this interesting tendril effect by bringing that hole size down. If we increase that max hole size, then it's going to be less pronounced. But yeah, look, we've managed to get some holes developing there. And look, if we carry on playing but start reducing this density, you're going to see that we're starting to develop more holes as the sheeter is disqualifying some of those particles for sheeting because they no longer have a high enough density to carry on that sheeting process. Let's just put that back up and reduce that hole size down. So what you can see by making adjustments to just the density and the hole sizes is that these settings are incredibly interconnected. You have to see them all working together every frame and not think of them just working independently. They are all interconnected. So if we have a look at our max speed value, let's just switch our sheeter off for now, and let's just play through this sim. So we can see if we go to the emitter, to the emission tab, that the particles are coming out at 269 centimeters per second, and we have 100% bounce off, so they're bouncing off at the same speed, so they're maintaining that. Let's have a look and see exactly what our particle speed is, and we can do that by looking at using the XP console. So look, if we go to our X-Particles menu, and we can go to Utilities, and we can open up the XP console. There we are. And look, with our emitter highlighted in the Object Manager, let's go to the console and click Get Active Emitter. And now what this is doing is, for every single particle that is being emitted by this emitter, it's showing us the particle ID and the age. Now, they all got the same age because they're all shot out on the same frame. But look, we can go to Data to Display, and we can pick all of these different data channels that the particles contain. Let's go to Speed. So here we are. Look, here is our speed. And we can go down and see every single particle's speed value. And if you want to quickly see what is the minimum and the maximum speed, if you just double click anywhere on these, double click, it brings up the minimum speed and the maximum speed. So the minimum speed is 8.4 centimeters per second, and the maximum speed is 296. So with that in mind, let's go back to our sheeter, switch it on. And look, our maximum speed is 400 centimeters. So every single particle is being considered viable for sheeting because the maximum is 296. So they all fall within this max speed. But look, if we put this down to, say, 100, and let's hit play. Now only the slower moving particles are being considered for sheeting. And if we put this down to, say, 20, we're not getting hardly any sheeting at all. Let's move it up to 83. And now we're getting more, but it's disqualifying some particles. And you're seeing particles on the extremities now. These could be like droplet particles, which aren't sheeting because we've reduced the maximum speed. However, it is often useful to keep this maximum speed quite high, to include every particle. And that's because we have an extra relative speed check, which can be easier to manipulate to get the looks that we require. So what we're going to do to explore both relative speed and some of the other settings that we haven't looked at just yet is we're going to adjust these settings back to where we had virtually a continuous sheet of splash. So to do that, what we will do is increase this max hole size up to about 20. Let's hit play. And there you go. So we're getting this continuous stream. Now, if we continue playing this simulation, it's just going to keep going and going, and this will become an ever-expanding sheet that will never, ever stop growing. And if we just come round to this angle, hit play, you will see, and that is because our original particles are moving outwards, and our sheet particles, all of these new particles which are being created by the sheeter, fit within the threshold checks that we've put. So it just keeps creating new ones and new ones and new ones, and it will never end. It will just keep going and going and going. And obviously, in many situations, that isn't what we want. Now, often when you're making splashes like this for a product shot, it doesn't actually matter, because usually you'll only play a few frames of it, the initial impact, and then some of the splashing, and then you would cut away. You very rarely, if not ever, animate the entire splash dying out. But let's just say that we don't want this just to be continually creating this sheet. How can we avoid it? Well, one of the things that we can do, there's a couple of things. We can do what may be the obvious first choice, which is checking the age, so only allowing particles to sheet for a certain amount of frames before they stop. So let's just explore that one first. So if we hit check age, what this is saying, let's just remove the variation for now. What this is saying is any particle can only sheet for the first 60 frames of its life. Let's put it down to, say, 50 frames. And let's see what difference that makes. Hit play. So we get our sheeting as we would expect. But look, as the playhead comes through to frame 50, they're no longer allowed to sheet. And they start breaking up. And so then if we run that same, let's put it down to 30 frames just so it happens a bit more quickly. And let's put an equal amount of variation to the actual max. So this should give a much more pleasing end to that. And then, yeah, look, so it's kind of breaking up much more organically now you put that variation in. So that's one way of splitting it up. But we could actually do something different here and get a bit more of a natural looking ceasing of sheeting. So let's just switch that check age off, and we're going to actually use relative speed here. So what we're going to do, let's just look at it before we do relative speed. Hit play. Now, these particles at this part of the lemon, especially the newly created sheet ones, are not moving very quickly at all. And if we go back to our X-Particles Utilities console, double click on our speed, look, our slowest moving particles are only moving 2 centimeters per second, so not very fast at all. So what we can do is go to our relative speed, and say only particles which are moving more than 10 centimeters per second relative to each other can be accepted for sheeting. So now if we hit play, what you're going to see is there are still, right, so we haven't got that speed amount high enough. There are still enough particles moving just above 10 centimeters per second to have an effect. So let's go higher. Let's go to, say, 20 centimeters. And what we're trying to do is stop this very slow moving particles from sheeting. Yes, look, we've got a hole here, but still it's too great. We're starting to get a hole here as they're moving more slowly, but they're still moving quickly enough. There are enough particles moving quickly enough to be considered for sheeting. So let's make that an even higher minimum speed. And then we've got a hole developing, but these ones are still moving fast enough to sheet. So let's go up to, say, 50 centimeters. Go again. And there we go. So now we've got a hole. And we haven't got that kind of self-generating endless sheet of particles. All right. And what we could do is obviously do that in conjunction with an age check. So let's put this on, say, 60 and 50. So we're getting this nice hole. And then eventually they will stop that ever-expanding sheeting as they're told they've got to that age where they're not allowed to sheet anymore. And we're getting this kind of disintegration of our sheet. Let's switch off that age check. So the minimum maximum speed threshold is a useful tool, especially for stopping slow moving particles from just continuously making a sheet. In this instance, let's just try putting that up even higher. Let's put it up to 80 centimeters. And there we've got this nice hole coming out. So now it feels more like that original splash of water has just been splashed out, and we're not creating thousands of new particles all of the time. Okay, so that's a nice look. So let's now explore how we might get some more interesting looks from this sheet. Now, we can start exploring our velocity alignment. So what velocity alignment does is it adds an extra check to the two particles that are moving away from each other. And that check is the angle at which they are moving away from each other. And what this says is, if we just activate velocity alignment, what it is saying is it will only allow the two particles to create sheet particles if all of these checks are satisfied and they are moving under 30 degrees of angle away from each other. So if we hit play, you're going to see an incredibly different simulation here. Let's hit play. So now look, we're getting these really interesting splash spikes. And that's because it's not allowing particles that are moving more than 30 degrees, an angle greater than 30 degrees away from each other, and that enables us to get these much nice kind of spiky looking tendrils in our splash. If we increase this angle, obviously you're going to have fewer and fatter tendrils. If we reduce it way down, you're going to have much thinner tendrils. That's a really interesting look. And again, remember, all of these checks are kind of interdependent. And so look, if we have massively reduced the angle at which we are sheeting particles, we can afford to increase this max hole size. And we're not in danger of it suddenly wanting to sheet everything, because we're checking for the angle at a very kind of low degree. So if we now increase this hole size, it just means that we're hopefully going to get longer tendrils. Let's have a look. So it's able to sustain that tendril for longer because we've increased that hole size. And we can kind of do that safely without it going out of control because we have such a tight angle here. So that's looking really cool. Let's take off that relative speed check to see if we can get some longer tendrils. Yep, so now we're getting them for longer. Let's reduce this angle even more. So that's looking nice. So as you can see, as we start mixing these various different checks, we can get hugely different looks from one simulation. Now, earlier we set up the emitter to have its default surface tension. And what we really want for these macro high-speed photography style splashes is that we need a kind of a thicker leading edge, and we need these waters to start forming droplets, and that look is achieved via surface tension. So let's go to our emitter. Let's go back to our extended data tab, and we're going to increase our surface tension. Let's ramp it way up by a factor of 10. Let's put it on 30. And what you're going to see is we're going to start forming much more droplets. You see, we've got more kind of globules at the ends of these spikes, and that is what we want to get this convincing macro photography look. And we could even ramp those up a little bit more. And what we can do to actually help this process along a little is we could also add some drag to the atmosphere, because at the moment obviously this is like it's being simulated within a vacuum. We've got no forces in here at all. So let's go to our modifiers. We'll go to our motion modifiers and let's put in a drag modifier. And by default, it's set to air with a force multiplier just on 100%. So this is going to force a bit of drag to a certain degree, but it's not going to make a massive amount of difference because we're effectively simulating a slow motion splash in real time. So what we really need to do to get that proper effect of this drag is to increase this force multiplier. So we could do one of two things. We could falsely make the atmosphere in which this fluid is moving thicker, and we could do that by changing the density. The default's air, but we could change it to something really thick like moving through water or carbon dioxide, but we'll just keep it on air, but we'll just increase the force multiplier. So let's increase it by a factor of 10. Hit play. And now we've got a bit of drag in the scene, and it's just going to mean that we're going to get these really nice surface tension globules just happening a little bit more quickly. Now you can really see the effects of that surface tension. Look at this rounded edge and this more kind of bulbous tendril, and that's looking really cool. All right, so we have gone from being able to create a thin sheet. We can change how many of those particles are sheeted with our various different checks like density, hole size, we've got speed, we've got relative speed, we've got age that we can stop, we've got velocity alignment. Just finally, we have a setting called remove sparse. Now, for most uses, you will not need to use remove sparse, but to demonstrate just how it works, let's just reset some of these values. So we'll remove velocity alignment. We will reduce our max hole size down a little to say 20. And let's just take off that drag for now. And we'll hit play. So now we have got our thin sheet back, which is much more kind of continuous. Let's just reduce that max density down a little bit further. So we'll get a couple of holes in there and it'll look a little bit more interesting. All right. So we have a setting called remove sparse, and this is for when the sheeter creates particles and those sheeted particles are created kind of almost too much in isolation of the rest of the simulation. They'd be considered a sparse particle, and they might not look very good within the context of your simulation, and they may not mesh very well. So you kind of want rid of them. We don't want sparsely spawning particles. For most scenes, you will find that you won't need to use remove sparse, so only include this if you are getting these sparsely spawning sheet particles. Now there are two checks that are done, two sliders to set for this. The first one is a minimum distance, and what it says is this: it looks within this minimum distance of 10 centimeters, and if there are no other particles within this minimum distance, then it considers itself a sparse particle because it has no friends within this minimum. So therefore, if it is a sparse particle, it is a candidate for being deleted, but it then has to do a density check first. And what it's saying is, if the surrounding density of this sparse particle is greater than this amount, it will be deleted. If the surrounding density is not greater than this amount, it won't be deleted. And how that works is, effectively, the higher this slider, the less likely it is to be deleted because most of the density is within it. The lower this slider, the more likely it is that the particle will be deleted because it's much more likely that the rest of the surrounding area has a higher density value than this. So let's have a look at how that might work. Let's put this density value onto 0. And that is saying that it will definitely be deleted because every area in the simulation has a greater density than 0. So if we hit play, it's getting rid of virtually all of those. So obviously only the particles that don't have another one within 10 centimeters are being deleted. If we reduce this, you're going to see an even more aggressive deletion. They're virtually all gone. If we increase the minimum distance to 50 centimeters, we're going to see some sheeting, but we're seeing some deleting as well because obviously we have this max density value set at nothing. So obviously it's going to delete. But if we increase that up to, say, 50% now, you're going to see much less deleting of those particles. We can see there's a little going on, but it's much more looking like the original simulation. So in this scene, this isn't the correct tool for us. By having removed sparse, we're actually creating sheet particles within this sheet here, and we're deleting some of those within that sheet, and we're getting this what looks like flickering, and that's not what we want, and it's not what this function is intended for. So only use if you're experiencing some sheeting appearing kind of outside your main simulation sheet body, and you want to get rid of those. So you can do by reducing that min distance and adjusting the maximum density value, and then you will be able to get rid of some of those particles, which will then be considered sparse, which means you're going to get a much more smooth simulation. So let's deactivate that, and what we'll do is let's just get our simulation back to that interesting look that we had achieved with our velocity alignment. Let's keep that on, and let's hit play, see what we're getting. Need to increase our density because we had lowered that. Let's have a look. So that's looking pretty nice. I'll increase that density up a little bit more. Perhaps increase this hole size. All right, so we're getting some pretty nice looking tendrils there. In fact, let's just give ourselves a little bit more to play with. We'll increase that velocity alignment angle. So we've got some kind of wider tendrils to play with. We'll put our drag back on as well. And that's looking pretty cool. All right. So there's another couple of things that we can do within the sheeter which can give us some nice effects. So let's go to our modifiers, and we're going to bring in a bit of turbulence here to create some interesting motion. So we'll go to our motion modifiers menu, bring in a turbulence. Let's reduce this scale down a bit, and we'll put it on a fairly strong amount. It might be too strong. Let's have a look. All right, so that turbulence is affecting our particles. And we're getting some pretty kind of interesting noises to our splash here, which looks, I mean, there's some very nice detail there. But it's starting to get very noisy in these different areas. In fact, to highlight this, let's just adjust our sheeter somewhat. What we're going to do is we're going to increase our velocity alignment. Just switch off the turbulence and the drag just so we can see this is happening. What I'd like to do is create a bit of a thicker sheet. So that's looking pretty nice. We could maybe reduce the max density, which will give us a hole or two. Yeah, and then let's just reduce that angle slightly. So I'm looking for kind of a star shape with some nice points, but with some nice thin sheeting as well. And that's looking good. Okay, so let's go back to our turbulence. So we'll put our turbulence on. And of course, all of the particles are being affected by this turbulence, both the sheeter particles and the original particles. And we're getting a pretty nice effect. If we increase that turbulence strength, it's going to start getting a little out of control. Because obviously the particles are moving, which is changing. They are being sheeted as well. And it's all getting a little bit messy. I mean, it's a nice look. But it's losing its water-like feel. But what would be nice is if we could have the original particles affected by this turbulence, but not the sheet particles. So our sheets remain unaffected by this very noisy turbulence. How might we achieve that? Well, we can do that using particle groups. So to get this set up, let's go to our emitter. We're going to go to the Groups tab, and we want to create 2 particle groups. So we're going to hold Control and click Create and Add Group once and twice. So now we've created 2 particle groups. And what we want is we want the emitter to only put the birth particles into Group 1 and to ignore Group 2 for now. So let's go to the mode and change it to first group only. So now what's happening is particle group 2 is doing nothing at all. All of the particles are being put in particle group 1, and you'll see that our simulation looks exactly the same. But here's the cool bit. What we can do is then go to our sheeter dynamic object, and look, there is a group window, and we can put in particle group 2. Now, what this is saying is the emitter is birthing the particles and they're being put into particle group 1. But then when the sheeter creates its particles, they're being put in particle group 2. So then let's go to our turbulence modifier. Let's go to our groups affected. And let's just put in both. But let's say particle group 2, we don't want to be affected by the turbulence. So now we're going to have a different look. The original particles are going to be moving around with that aggressive turbulence, but the sheet particles aren't. And it means that we're able to maintain these really nice, thin sheets of fluid, but our original particles are being moved by that turbulence. And what we get is these really nice kind of surface tension veins running through our splash crest. And that's a really nice technique. And we can go really aggressively on that turbulence now because it's only affecting our birth particles. Our sheets aren't going to be heavily affected. And you can see that we're getting those nice, smooth, filled in sheets of fluid, but we've got this really angry, pointy, noisy veins which are outlining that fluid. That's a very interesting look, and we're able to achieve that look by separating out the 2 particles. The birth particles are in group 1, the sheeted particles are in group 2, and then we can tell different modifiers to be affected, to affect either or both of those groups. So if we play that through, we can get these really nice stylized looks pretty quickly. using the effects that we're getting from our different modifiers affecting this splash, and only getting some of the particles and not others. And finally, let's just explore a couple more settings that we haven't looked at yet. And now we've got our particle groups set up, we could have a look at this option, which is right near the top, Interpolate Properties. So to demonstrate this, what we will do is adjust our particle groups a little. So particle group 1, remember, is our original X-Particles emitter particles, and they're being coloured via a gradient. So let's just change that. We will set this to be just a single colour, and we'll make them, let's make them bright green. And then particle group 2 are our particles created by the sheeter. So let's change those to a single colour and make those bright pink. Okay. So if we go to our sheeter, what Interpolate Properties does is it interpolates the properties of the surrounding original particles so that the new sheeter particles are born with the correct, with the appropriate properties for its position within the sim. And so by that I mean, let's just switch off Interpolate Properties. So there's no interpolation going on at all. What you will see is that the original birth particles will be green and all of the new sheeter particles will be pink. There is no interpolation of particle property going on. These are pink, these are green, and that's the way they remain. However, if we interpolate properties, what you'll see is each sheeter particle, its properties will be interpolated dependent on the surrounding original particle properties, which means that they will be turned green effectively. So if we hit play now with Interpolate Properties on, the sheet particles are green also. So that is what that Interpolate Properties is doing when you have separate groups. But it does more than just interpolate the colour value. If we have a look in our particle groups, it will also interpolate the other particle properties. So to view that, let's change this group from the standard mode to the extended. And by doing that, it lets us adjust the physical properties of the particles. And so with Interpolate Properties on, the sheet, it will also interpolate all of these physical particle properties as well. So if your birth particles have varying temperature values or fuel values or even user-defined values, these properties will then be interpolated, and our new particles within the sheeter particles will have the correct properties dependent on its position within the simulation. So that is what our Interpolate Properties does. And then finally, we have a separating only option, which is on by default. And this just means that particles will only be considered for sheeting and have all of these checks done if they are moving away from each other. And in 99 cases out of 100, you want them to only sheet separating particles, which is why it is on by default. But if you want every single particle considered for sheeting, whether they are separating or not, you can deselect this, and then that will happen.